Right. Second example problem. We got the old snowball melting. Now you're gonna have to have a little bit of a suspension of disbelief here. A lot of physics applications, we kind of ignore a lot of things, like the fact that if a snowball was melting, it would not remain perfectly spherical. But we're just gonna pretend like this is gonna happen. It's a magical snowball. So here we go. A snowball is melting at a rate of 2 cubic feet per hour. Cubic feet. So that must mean we're dealing with volume, right? 3 dimensions, 2 dimensions area, 1 dimension, you just got like a distance or a length. 3 dimensions, 3 cubic feet cubed. It means we're dealing with volume. So the snowball is losing, is melting at a rate of 2 cubic feet per hour. If it remains spherical, which it would never would, but we're just going to pretend, at what rate is the radius changing when? When r equals 20 inches. So we're going to wait. We will wait on that until after we take a derivative. All right, so let's see what we're going to do on this problem. Let's move over. And you can see we made ourselves a little circle, but turn it into a sphere, and we can pretend that this is our snowball that will be melting. Now we're going to need to know our formula. The formula for a sphere. Do you know the volume formula for a sphere? Well, good thing you're now on an online class, so you could look this stuff up if you ever forgot. So we'll say that the volume of the sphere, the volume of our sphere is 4/3 pi r cubed. All right, well, this one doesn't have a lot of variables in it. I don't even know what to do. We found ourselves an equation. What do the rules tell us to do again? What do we need to do? We need to draw a picture if possible. Oh, we got to go get the rates. Shit, I jumped all the way to the equation. Now, this is just a suggestion as to how we go through things. And I will sometimes go out of order, but always refer back if you have any questions. Oh, let's jump back down. All right. There we have it, 4/3 pi r cubed, but we need to start defining those variables. Let's see what we got. So it says that a snowball is melting at a rate of 2 cubic feet per hour. I think that's the change in the volume, right? Because cubic, with respect to time. So we're saying that it's losing. So here it is. It's negative. And we'll say 2 cubic feet per hour. So we're losing 2 cubic feet every hour. Okay. Now we also have that little radius, that thing. We want to know when. So at what rate is the radius changing? Oh, that's the question. That's what we want to know. What's dr dt? That's what's wanted to know. We want to know how fast is the radius changing with respect to time. How fast is that thing shrinking as the volume is shrinking? When our radius is equal to 20 inches. But have you seen the issue we have here? We have 20 inches, but we have cubic feet. Now we could change the cubic feet into cubic inches, but that is going to be a huge pain in the ass. Huge pain in the ass. Now changing linear things into feet, that's not a big deal. So why don't we just jump through and just convert this into feet? So I think, how many inches? There's, 12 inches in every 1 foot. So now when we do that, our inches, they just cancel out, and it leaves us with our radius is equal to 20 over 12. That's 10 over 6. That's 5 over 3 feet. So 1.6 repeating forever feet. When? So we'll plug that thing in at the end. So now we have our equation that ties our volume and our radius together. We have our dv dt. We have our dr dt that we're looking for. And we have our when. Okay? Let's take care of this problem. So let's take a derivative on our equation. Let's go. So we're going to say, what's the derivative on v with respect to time? It's equal to the derivative on v with respect to time, nothing else, times 1 if you'd like, right? Because the derivative of just a single variable would just be 1. Now we go through and we're going to take a derivative on 4/3 pi r cubed. Well, that 3 is going to fall to the front, or it's going to cancel. We're going to lose a power. So we get 4 pi r, and it says lose a power, squared. But every time we take a derivative on something that could change, some sort of variable, we need to make certain to put in the derivative on that variable r with respect to time. Well, there's our formula. So this is the point where we start taking everything with a dot, plugging it in, and just saying, can we solve it? So instead of dv dt, we have it. It's -2 cubic feet per hour. Now I'm not going to write in the units along with this. I'm just going to put in a -2. We'll get it all at the end. Is equal to our 4 pi, and then our r squared. Well, our r squared, it told us to wait until after we were done with our derivative. So we waited till afterwards, and we're like, all right, here it is, 5/3 feet. And then we need to go find our dr dt. That's what we're looking for. And this is awesome because it's the only variable that's left over. Let's do a little bit of algebra. We clean it up, and we're going to go get our solution. So we have our -2 still outside there, and then we're going to have our 4 pi times, what's that? 5 squared is 25. 3 squared is 9. So what's the times our dr dt? Let's keep cleaning. We put that together. What's that? 100 pi over 9 times our dr dt is equal to -2. Well, let's multiply by its reciprocal on both sides. 9/100 pi. And I think we're going to end up that our dr dt over derivative on the radius with respect to time is going to be, that'll cancel out. What are we going to get? -9/50 pi. And what's our units? How fast would it be changing? Well, we're dealing with feet, right? So that would be feet per what? Feet per hour. And that's the solution to our problem.